Hello everyone, this is Michael Joseph with XRF Group Melbourne Analytical. Today we're going to go over SuperQ6, making an application and creating a calibration from that application, and then creating a drift monitor for that calibration. When you first launch the SuperQ6 software, you're going to be prompted with this screen here. This is SuperQ6 Manager window. What you see here is Measure, Applications, SPC Results, Spectra, System, Virtual Analyst. Today we're going to only be focusing on applications. In the future we will have videos describing the rest of these other modules here. In the top left hand side you see 3 dashes. If you click there, we have a database compact. This is useful when you start to generate more data from your measurements. It's useful to compact the user data file. And if you don't, or if you forget to compact here, the software will prompt you to compact. When it does, you should say yes. This will make everything more efficient and tidy things up on the back end for all the files. Database maintenance, this is where you can set up the database to be saved as a backup. We generally prefer to do this manually rather than to rely on the software for this for various reasons. Database update is if you're going from an older software to SuperQ6. So if you're on SuperQ5 and you want to come to 6, you can go ahead and do database update, and it will update your database from 5 to 6. Language configuration, type standardization. For those of you that have used type standardization in the past, it is present here. If you have more instances of the manager open and you want to close them and you're not sure, go ahead and hit end all SuperQ processes here. There's a help button and an exit button here. So once you hit applications, you'll see this window here, and we're always going to start in the top left and work down. That's generally how the process goes here with SuperQ6. So let's start with standards. When I open standards here, I already have a lot of standards already in here. If you don't, you might not have any. That's okay. There's an import button here. If you hit the import button, you can upload an Excel file. If you don't know how to configure the Excel file in order to be compatible with the SuperQ6 software, that's okay. If you hit F1 and you go to search, import, there is a demonstration of how you need to configure your Excel spreadsheet in order to import your standards if you wish to do it that way. So let's start off with a brand new standard. I'm going to say that this is standard, and we're going to call it test 1, and we're going to be interested in concentration application only, not interference, Compton, or X or D phase. Next, let's go to concentrations. So I see there's some information here, but we don't have anything in. We could manage compounds here, but I generally like to go to the details and fill that in with these tabs here. So let's start with the sample details. We're going to let's try a pressed powder for this application. You do not have to put detailed information in here. However, it is very important if you wish to apply certain corrections at the end during the calibration for various matrix models. So let's go ahead and enter. The more information we give the XRF, the more results that we can play with at the end as far as calibration corrections are concerned. So let's say, for example, 32 millimeter thickness, let's say 4 millimeters. Sample weight, let's say 5 grams. Let's say we used a binder. Let's say we're going to use a wax. Let's go wax. And we'll go 1 gram for the wax. So we have 6 grams total. Perfect. Composition. This is where we can add compounds. We can add them one by one if you want. And you can come in here and say what it is and fill the rest of the information out. I don't like to do that. It's kind of slow. So what I'll do is say delete that one. I'll go to manage compounds. And in here, things are generally a bit faster. Now on your compound list, if you have none selected, the default is elements. So if I select it, it's going to put the formula as an element. Okay. If I go to geology and I hit aluminum again, now it's going to give me a mineral formula. And if I go to system, aluminum's not a good example, but if there were more aluminum oxides or other compounds, they would be listed here. However, if you want to add an aluminum compound that's not shown here, you can do so. If you go back to the house, go back down here and go to compound lists, you can open up the system and you can annotate and add, or you can just make a new one and add whatever you want to that. And when you come back to add compounds, they should be listed here, and you should have, if you added a new compound list, the list name should be here as well. For this application, we're just going to keep it simple and go with the elements. So what this is doing generally is it is going to just do a conversion from aluminum to aluminum oxide if that's what you choose to do. It's simply conversion. It's not measuring aluminum oxide. It's just doing a conversion to aluminum oxide. So we have aluminum, Si. Let's just go with some of the basic elements here for this application, and maybe a few that aren't so basic. Uranium, maybe lead, for those of you doing some interesting things here. Maybe barium. And then say we'll just say okay. So now with the table here, we have concentrations, we have units, so you can switch these to anything you have here. We can go to ppm if you wish. I'm going to keep everything in weight percent just to keep it simple. So let's just keep it there. And then quality is going to be either low, high, or calculated. High quality are going to be coming from your certificates of analysis for your standards. Some of those certificates do have things that aren't certified on there, so if they're not certified, I would mark them as low quality. Generally those ones you don't want to add to the curve, but it's nice just to see where they come out on the curve. So it's not bad to include them. It's not bad to see where they are, they're just not certified. So we'll leave everything as a high quality for now, and then we have the elements and the element concentration. So let's go here. I'm just going to put some random numbers in here, nothing specific. I don't have standards on me, so let's just make some things up, which is okay. Okay, so when I click off here, now the sum is going to be 31.677, and we get a warning sign. The warning sign's indicating to you that you're not really telling the instrument the standard's complete chemistry. In order to produce a good curve, produce good matrix models, and to even use matrix models, certain matrix models, we need to know at least 98% or more of the composition of the standard. So for this example, what I'm going to do is I'm going to add a compound, and let's say that the standard is carbon based, okay? So let's just say carbon, and then I'm going to toggle it as a balance over here. This could be something similar to what you guys are using now. You may choose to actually not measure something that has a high concentration, maybe a metal that has like 70% copper or something. Maybe you just want to do it as a balance. Maybe the count rates are too high and you don't want to damage your detector. That's okay, you can force it as a balance. In this example, I'm just going to use carbon, and we'll force it as a balance. So now our sum is 100%. If I go to the general tab, here I'm just going to say test 1, and I'm going to leave this as is, and I'm going to say save all, and it should save test 1 standard. Now you're going to do this, and you're going to add for all your standards. You're going to go ahead and create new standards and put them in here for everything. So you should have how many ever standards you have available, maybe 5, 6, 7. The more the merrier, the better statistics. So for this example, I'm just going to have the 1, and we're going to move on to the application itself. Here, let's go to new application. I'm going to say compound application new. And on the very first tab here, we have information. I'm going to put in test 1 application. Obviously, you're going to have something more precise to what you're doing, and I might fill in the information saying I created this on this day, which is the 5th of March, and we're going to say I'm interested in iron, uranium, lead, and you can fill in more information so your colleagues know why you made this application and what it's used for. Next tab down here, we have the identification scheme. This is useful if you have a limb system. You can go in here and identify sample name or more things if you want to add fields. You can load identification schemes as well if you already have them from previous instruments. You can save them and put them on other instruments if that's what you wish to do. These will be in the measure and analyze screen, the sample changer window, when you go to run a routine sample for this application. Conditions. We are going to set this application up for a vacuum. If you have helium, such as liquid samples, powder samples in a cup, you're going to run things in helium. You will never run them in a vacuum. We are going to say collimator mask of 27 millimeters. The reason we are saying this is because the samples are 32 millimeters in diameter, as we specified back here in the sample details of the standard. So let's go ahead and say 27 millimeters. I'm going to bump this up a little bit. Go to 10 seconds and 4. Just a little easier on the hardware there. Vulnerable sample would be like your liquids and your powders. We're not going to turn that on. We will keep the spinner on. The measurement execution, so our sample cup is going to be a 27 millimeter for 32 millimeter beads. Our priority is going to be normal. And our default archive will be the name of the application. We are going to look at the conditions, WD obviously. The system here has an ED as well. Not all systems do. We're going to keep it WD, and we're going to optimize for sensitivity rather than resolution. So I'm going to go ahead now and say save as. I'm going to say test 1 is the application, save. And as soon as I save it as test 1 application, the default archive is populated with test 1 as well. This is very useful to keep it individual to the actual application. You do have the option to change it and put it somewhere else. That's okay. But I do not recommend that, because if you do and your archive becomes corrupt, it means that you lose all the data for all applications rather than losing data for only one application, if that's what's going to happen and you don't have a backup. So let's keep it as the name of the application, and all the data that's ran will be saved in this archive. Okay. Next we have sample details. Again, this is the same thing that we filled out here in the standards, sample details. So we don't need to do this again, and quite frankly, all the standards might not be the same. Okay. So you don't want to fill this out. A better route is to go here and to put all the information in the standards. The standards might be different thicknesses. You might even have different diameters. That's okay. You can still run them and use them as on the curve. But don't identify them here, because not everything is going to be the same. Okay. They might be, they may not be. If we go to standards field next, let's say include standards. Let's go to test. So I made test 2 earlier today, so we'll include 1 and 2 as well, just for this example. And here it's very important on the compounds tab to hit calculate sample. Calculating sample is going to give the instrument a max and a min of the sample standards for each element. It's also going to generate the channels that we need to use for each element. Okay, so now we can see a min and a max, and this is used for calculations of various functions during the calibration. And you can see here we have analysis, which means these are going to be measured. You could have it fixed if you wish. If you know if it's a synthetic and you're pretty sure that that's what it was, you can say fixed. You can have a manual entry, and you can have a balance, which we do. We have carbon. Okay, so we're good here. Let's move on. Let's save it. I always like to give a good save, so I don't lose progress while we're creating an application. So the next tab here is channels. So go to channels, and the channels are going to be generated for us, and these are going to be defaults. Okay, there's nothing wrong with the default channels. The one thing that stands out to me, we can go over here, is the crystal for this one, but we'll get to that in a second. Let's start with the name. So we have obviously the name of the element. Next here, the line. So you could have different line groups. So right now we have things set up for K alpha 1, 2 and L alpha 1, 2 for the heavier elements. You could simply click on that and go for a K beta if you wish, or you could parse it out from doing a sum of a 1, 2 and a 1, 3 and go for a 1 or 2, a 1, a 3, a 1, a 2. So you can play with the lines. You might have overlaps. You might have a lot of intensity from a certain element, and you might not care about K alphas. You might want to use a K beta. Perhaps a K beta is not giving you overlap issues, so then you could use K beta if it has high enough intensities, and you won't have to worry about a K-alpha overlap with another element if that's the case. So there's various things you can do in here to get away from line overlap issues, or to reduce background, which increases your signal to noise ratio, which is helpful for the overall accuracy and precision of the calibration. So here we see we have the power function here. We have these. Generally, we don't play with these. In certain cases, you may have to. Filters. We can apply filters to things that have very high intensities to cut the background noise, and to save the detector if there is very high intensities going to the detector. Crystals. There's various crystals here. The one that stuck out to me right away was the silicon. So let's change that. So right now we have a big overlap potential. So if I hit sort things by 2 theta, we see that we have 2 peaks pretty much right on top of each other, and we don't want that. So let's change this one to the PE crystal, and now we're at 109, so we are away from 144. And let's just leave everything else as default, okay? So let's move on. Optimizing conditions. Very important steps here for the calibration. You're always going to want to use the highest concentration standard, highest concentration element, to do the optimized conditions, okay? So for aluminum, if I were to look at standard test 1 composition of aluminum, I said 5%, okay? And let's go back here and open up test 2 and see what the concentration is for aluminum. 24. So I would use test 2 for aluminum when I go to optimize the conditions, okay? So you always want to use the highest peak, the highest concentration standard that you have for each of these elements. And you'll work through each of these elements here. Not necessarily in order that they're listed here. You should just be pairing the same standard that has the highest concentrations for various elements. So if we look here, let's say phosphorus is 23% and phosphorus is 0.05. So again, I would use test 2 for aluminum and phosphorus, and so on and so forth, okay, to work through these. So for this, I would always start with the PHD. This is pulse height distribution, or pulse height detector. This is basically the energy that's going to the detector. Each detector might be a little bit different here. So flow detector on this one, for example. And what you want to do is when you first run this, you're going to get a peak and you're going to get bars of energy. So let's go ahead. I'm not going to do this now. I'm not connected to a spectrometer, but we can take a look at an application that's already been done. So let's look at some Oxy 27. And we go to optimize conditions. Let's go straight away to aluminum, just for example here. Okay, so if you run the check angle first, if you measure the check angle first over here, that's okay. But then if you go to do the PhD next, and you notice these lines that are out here, they're not snug. You want to make these snug up here, because you don't want to include this background noise into the signal, okay, that's going to the detector. We want to cut that off. So if I make changes to the PhD, having run the check angle first, I just change the conditions, and now I have to run it again. So it's more efficient to run the PhD first, make the changes I need, then run the check angle next, okay? So PhD first, then the check angle, and then the line overlaps. And you can see here line overlap order. You have line groups 1, 2, 3, and 4. I'm not interested in 4, 3, or second order line groups. I'm only interested really in the first order line groups for this application. And right now for aluminum, K alpha 1, 2. So we're seeing the peak. That's where we should be. We're pretty much close, almost right on it. Not a big difference, not a big deal. These are theoretically where we should be based on the crystal and everything of that nature, the 2 theta angle. So we're pretty much close right to where we need to be. This is just the sum peak of these two. And then we have satellite peaks, aluminum satellite peaks that I'm not worried about. The reason why you want to check the line overlaps first before you do background selection is because you don't want to put a background right on top of a line overlap if there is one. So this example, aluminum satellite peak, I would not flag. If this was something else and there was a big peak here that was interfering with our main sum peak, or 1, 2 sum peak, then what I would do is I would flag that line, and you would simply go here and say flag. Let's say it was some other element. Would it be bad to put a background right next to that flagged line? You would want to put that background a bit away from that position, okay? So always check the line overlaps first and make sure you're not putting a background on that position. Next is picking backgrounds. The general rule of picking a background position is if the peak is greater than 10 times the background position, then you generally don't need to place a background in. If you're on the fence, it's always better to put one in because you can always remove it when you're done. Add it or remove it when you're done. If you don't put it in and you do the calibration and your D value is slightly higher or lower than 0, and you trace it back to the backgrounds when you're optimizing the condition, you could come back and put it in, but if you put it in after running the standards, you'll have to run them again. So it's better to put them in and then just to turn them off when you're doing the calibrations. So here, another thing, there's 2 positions here selected. Generally, we like to only use 1 background position instead of 2. There's just less room for error. And then we always like to look at intensity based as well. You can make a selection based off intensity based, so the position here right on the peak. Okay, so you can do it position based as these 2 are, or you can do it intensity based, or you can do a mixture. Okay, you can take this one out and you can keep the intensity based one in. I'm not going to save this because it's already been done. So once you're done selecting background and overlaps, we can go to the times tab, and in the times tab we need to calculate what the detection is and what the total runtime is for the peak and the backgrounds together. So first we'll start off with the measurement, and we'll say what standard you use. Okay, you don't have to put the standard in, but it's always easier because we do need to know the concentration. You could manually put the concentration in, but it's always better just to select the standard because it knows what concentration was used. So for here, we have different options. You might be interested in absolute error, you might be interested in LLD, you might be interested in peak time or total time. These things are going to be selective for various labs for various reasons. Some people are concerned about total runtime, and some people are more concerned about error. So it depends on what you guys are interested in. For me, I'm going to say fix LLD. We'll start with 1 ppm for this example, and I'll say over here on the calculate measure time, I'll hit calculate measure time, and it's going to give me a time that's it's going to need to get down to 1 ppm on the peak in the background. So quite high. I don't want to run my application that long for aluminum. Okay, so let's go to 100 ppm and see what we get for time. So it's 4 seconds. Okay, let's cut this in half and see where we are. Again, 4 seconds. Cut it in half again. 4 seconds. Okay, let's try 10. 8 seconds. Okay, not bad. So let's go to 5. And that's doable. That's livable. 28 seconds for aluminum, no problem. All right, so I would say save, and then I would move on to the other next elements there that you have, maybe phosphorus, and go from there. Run the PhD, measure, move the lines in, okay. Run the check angle, see if there's any background or line overlap issues here. If you have some, flag them. If not, let it go. Go to background, put your backgrounds in, times, select the standard, select what method you want to do. We're doing LLD, calculate the time. Way too high for 1 ppm, so we'll say 100 again. See where we're at. That's pretty good, not bad on 5 weight percent there. Okay, so working through things like that, just work through all of them and you'll be done. The next tab here is status overview. Status overview is going to show you what's been done. It's a good little window to have in case you have a lot of elements. You might want to go ahead and add more. And just for the sake of things here, I'll do it in the test 1 application here. If I go to channels, you could go ahead and create channel. Let's say you are interested in running aluminum, maybe with a different configuration. That's fine. You can run aluminum in various ways here. And I could say just add a new channel. Okay. An element I would select as aluminum, and it's going to call it AL1. No problem. Add and close. And now we have 2 channels for aluminum. Right now they're set up to be the same, but let's say you wanted to make a change on the filter. You could run it with the filter. You could change the collimator. You could change the detector. You could change the crystal. You can change the power settings. You could change the line that you're interested in. So there's a lot of things you can do here with the channels. Okay, and again, it's just optimizing with the highest concentration standard for each of these. Now I go to aluminum, and I have an aluminum 1 as well, and you just work through all of these. Going back to the Sumoxy 27 application that's been done already, the next tab down would be quantitative program, and what I see here is I see all the channels including the background channels that are used, the times that are there. You can go in here and add change these times if you wish. You can also see the background method. There's various different methods you can do: fixed factors, calculated factors. You can use backgrounds to different channels if you wish. Acquisition, it's going to show you the acquisition for each of these. And generally what I do for the channels is I say sort by energy, which is important because it's going to do things in an energy stepwise fashion rather than going to a high and a low energy. It's just more efficient for the hardware. Okay, so at this point we are basically ready to do the calibration portion. So let's go in the let's go back to the house, and we'll go to calibration, and we'll go to Sumoxy. Notice here in the test 1, if I just hit calibration selection, you could go ahead and for test 1, and we can go ahead and open that up if you wish. But we're just going to work through this, going to the house and say calibration, saying new. If you have a new one, go ahead and create a new one there. We already have one, so we're just going to work through this Sumoxy 27 calibration. So general, again, information, go ahead and populate this, put information in the description for your colleagues, and then put in there what you did and why you're doing it, so people know what's going on with this calibration line, if you had any issues, so etc., etc. So now we just look at the overview of the standards. We see the standards that were used for the calibration. They're all for concentration. We can see the compounds that are there. Concentrations, we look at concentrations. One thing I always like to look at is the sum to make sure everything's been entered in properly. Sum for this one is 0, but that's okay because that's used as a blank. So then I just take a look at the details real fast, make sure everything's in there looking good. Okay, that's the blank, no problem. 100, so no big deal here. Just take a quick gander at these. And then I go to measurements overview. Measurements overview is going to show us that the standards were run. Okay, so we're at the portion where you don't have any measurements. Great, but we need to populate the measurements, so no problem. What we'll do is, let's go back here to test 1, and we'll go to, we'll open the test 1 calibration. So we're working through a new one. Okay. And if your standards aren't here, you could also load the standards. Okay, so find the standards that you had and go ahead and load them in, no problem. If you wanted to add them now and maybe you forgot them before, go ahead and add them in there. And then so you'll be here. So I have no measurements made. Okay, so what you'll need to do is go back to the SuperQ manager, open the measurement module. Once that opens, you'll go to the sample changer. At the top left, there's 3 cups. If the sample changer window doesn't open on it by itself, go ahead and hit those 3 cups, and it will open the sample changer window. Within the sample changer window, you will have a measure batch. Go ahead to the top tab there that says measure batch, and go to edit measurement. And in edit measurement, you'll want to pick the position of your tray, which will be A1. or maybe B2 or whatever position that you have available there. Go to A1 and say type standard. Run your standards as standards, not as routines. Run them as standards. Go ahead and put the application name in there. So for this one I would say test 1 application, and it should populate the standards that are available with this application, which we specified as test 1 and test 2. You can highlight test 1 and hit add, and then if you go back to the overview tab on the left, you'll see the trays, and you'll see that your standard test 1 has been added to position A1. Go ahead and do that for the rest of your standards. So position A2, type standard application test 1, and select test 2 for this second position, so on and so forth with the rest of your standards. Okay, when you're done, go ahead and say measure. Go back to overview and say measure, and it will measure your standards. Once the standards are done measuring, you will have populated your measurement overview window, and you should have all green checks. If you do not have green checks, there could be various reasons why. You might have an X, maybe there's an oversaturation error, or maybe the sample wasn't flat, or something happened with the hardware. It should give you an error. So let's move on. We have all the measurements. It's going to show when it was created. Perfect. And now we go to the calibration itself. Okay. When you have this done, you'll have yellow warning signs here. So nothing's been calibrated yet. And if I hit the calibrate button on the right, it's going to give me some options here. Okay. So right now everything's set up as FP, which is fundamental parameters for the matrix model. Matrix models are used to correct for absorption and enhancement effects that happen during XRF. Certain elements can excite other elements. They can absorb energy from other elements. So they can artificially enhance or absorb the numbers there and make the graph look a little bit sloppy. So what the matrix model does is it tries to correct for that. And there's various matrix models, but I always like to start out with none because I don't know if there's absorption and enhancement going on. I might have an idea that something may be happening there before I run the samples, but I'm not certain. So I'm going to say none, and then it also takes away the FP enhancement options here. And let's just go over these real quick here. In the standards, when we were creating the standards, I did say that if you click the enter weight and size information here, you'll have more options. So some of these options here that we're looking at now would be the use of the finite thickness effect correction and the FVG effect correction. If you do not know what these are, you can again hit the F1 button or this question mark down here. So let's just close this and then hit this question mark. And if I search finite thickness, it's going to come up with this window. This window generally is describing all the details that you're looking at here, but if I search this and then click on the top application one here and then go down, it's going to have a description of everything there for finite thickness and FVG. Okay, so if you're ever stuck, just hit F1 or this question mark and it should open this window, the help window. There's so much information in here, a lot of content information. It shows you how to create applications. It shows you the process that we're going through and helps you work through certain things. Okay, so very helpful. So in this instance, let's go ahead and say calibrate, and I'm going to say none, and I'm not going to turn on the finite thickness or FVG because I feel like our samples that were used here are plenty thick for the elements that we're looking for, so no issues there. And I'm going to say calibrate, and it's just going to calibrate everything with no matrix model attached. Okay, so there's various things we can play with, but first and foremost what I want to look at is to make sure that the status is green, so everything's good. Okay, you can go to details, you can look at the graph, you can go one by one and look at the graphs and see how, if there's any flyers, you know, something that you don't want to include, That's okay. So I noticed there was one here that was excluded. That one was way over there, kind of goofy. So it wasn't included. If you wanted to include it, you would hit include and you would hit calibrate selected. If you hit calibrate selected, it will only calibrate for iron and not everything else. So that's the way we should work forward here. So there's 2 points there, not just one. And if I zoom in, because I can't really, there we go. We can, if you left click and zoom in, hold it and draw a box, you can zoom in, and I can include that one as well. And now they're both included to the curve. If I hit this 1-to-1 button, I zoom back out, and now I see that the line is a bit skewed. So now, seeing that, I don't want to include those points, so you can hit include exclude F8, or for me, I like to work in this box, so I'll just exclude that one. Again, I'll zoom in just to see if I can get this one. So I'll exclude both of those. I'll hit calibrate, I'll hit 1-to-1, and now the line is like it was prior. Okay, so let's go back to overview, and for me, let's just work with iron. That's okay. The D value should be as close as possible to 0. This is essentially the background, whether you're including too much background or you're leaving too much in. So background selection is very important when we optimize the channel conditions, and we can see that we're very close to 0, although we're a bit negative there. Not too bad. And none of these really are that horrible. They're pretty good there. The E value is 1 over sensitivity. The lower the better. F value is a quadratic formula for the curve, which we always lock it. We don't like to play with the quadratic formula for the curve. That's kind of a fudge factor, so we always leave it locked, but it is there to be used if you so wish. RMS value, this is what I generally look at first and foremost for everything, the RMS and the D value. RMS, root mean squared, is error, and then we have relative error, and K, which is error propagation. Again, if you want to learn more about these numbers, you can simply hit the F1, and it goes into more detail about what these are. Okay, if I hit XRF theory, we look at the K value. Here's the lovely equation for the K value. So we started out with no matrix model, and the background is included. I like to play with these because, again, I don't know if there's absorption or enhancement for iron. I might have an idea, but let's just say, let's look and see. So the RMS is 0.097, okay? So let's say, let's turn on FP and see if our RMS gets better. Calibrate selected, 0.022. So it was 0.097, and now it's 0.022. So it is better with FP model, the D value as well. So let's go back and look at the details for iron. So we have a pretty nice line here. And let's see. I always like to look at the calculated chemistry there. Pretty nice. Pretty nice. Okay. So I would generally just work through each of these in that fashion. You could try alphas if you want. FP is a iterative theoretical based model. It is the most robust model that we have. Alpha's correct for absorption and enhancement, and that's it, where FP does a little bit more. And again, if you want to learn more, just hit the help button there, and there's more description. Sometimes it's not necessary to put on a matrix model. Sometimes none is preferred. But again, look at the RMS. So go ahead and play through each of these. So 0.7 for none, and if I go to FP, 0.72, so it's better on none. Try an alpha. Yep. So it's better with no correction for calcium. If I take the background out, let's see what we get. So background's not doing a whole lot there for the RMS, but it is changing the D value, and we are closer to 0 when we have it in. So let's keep it in. Okay, so let's just work through these and go ahead and look at the curves. You can include, exclude points. Go ahead and work through each of these, and then your calibration will essentially be done. Here we have line details. It's going to have all the information that we were already seeing in the overview window, so you can make changes here if you wish. It's going to have any overlap corrections if you have some, alpha corrections if you have some, and extended corrections if you have some. Standard measurements, so these are all the details. You can go ahead and look at things in count rates if you wish, calculated chem, etc., etc. Parameters, we should just leave these as default. If you want to learn more, just hit the question mark. It talks about each of these options here. So then you can go ahead and save it, and now you have a calibration. So you have an application that's been optimized in a calibration, and standards that you used for both the application optimization and the compound calibration. The next and last thing here for this video that we're going to talk about is instrument monitors. So if I go to instrument monitor, let's go to Sumoxi, which is the one used for this calibration. So the instrument monitor is used to correct for drift. You can also have it correct for different atmospheres. So if you're using something in helium and vacuum for the same application, you can go ahead and correct for the medium there, which is helium, or for the collimator mass change as well. Generally, it's used for drift correction of the application itself. So over time, drift will occur. The hardware will lose intensity over time, and you could experience drift as well from temperature and pressure changes. So go ahead and put the description of this drift monitor there. You can go ahead and put sample cup 27, perfect. This one's set to collimator mass of 37, that's fine. For our application, if we were using test 1 application, I'd put this at 27 millimeters because we said our beads were 32. The channels, if the channels are not populated here, we can go ahead and say load channels. For this example, let's just go ahead and create a brand new monitor, and let's just call it test mon 2. Okay, and I'm gonna say sample cup 27. I'm gonna say collimator mass 27, and I'm gonna correct for drift. We're gonna put all the instrument monitor data into the default archive instrument monitor. You could put it into the test 1 application if you wish, but let's just put it into instrument monitor. Save as. I'm gonna say test 2 mon. Save. Channels, it's not going to have channels, so I'll go to load channels, and I'll select the application that we were making, which was test 1, and I will if I click up here in the upper left, it highlights everything, and I'll say add and close, and it's going to add everything there for the channels, okay, that you used for the application. So then it's just going to import the check angle and PhD that you've already done. It's going to give you each of those in green for the PhD and check angle. It's going to tell you when that was last done. And it's going to give you the quantitative program, which is the channel information here. So for the instrument monitor, we want to set up either to correct for y-intercept, for the slope, or for both. Generally, it depends on the samples that you have available for your drift monitor correction, okay? So if you're going to use standards, that's fine. You could use the Osman bead that's provided. That's okay as well. However, what you're going to want to do is try to match your intensities. So the intensity of the drift monitor, you're going to try to match to the intensities of the standards used for the calibration. Okay, so if you have 10 weight percent and 1 weight percent for, let's say, uranium, it'd be nice to have 2 samples that represent the low and the high end when you're making these corrections. Okay, if you hit lock, if I lock this at 0, it means that whenever I make a measurement for the drift, it will not correct for the y-intercept. It will only correct for slope. So it depends on if you want to correct for the y-intercept and the slope based off of the standards that you're using to do so. In this example, I'm going to block the y-intercept and only correct for the slope. And in a lot of cases, that's all you will need to do. Next, I will go here and say add samples. I'm going to say Osman, just as a basic sample here, and I'm going to say add and close. I'll change this one to 10 and 4, and we're in a vacuum, 27 millimeter spinner will be on. We're not a vulnerable sample. I'm going to add another one. We'll just use that test one standard that we created earlier. That's okay. So test one as well. And we'll do the same thing. 10.4 vacuum 27 millimeters is okay. So now I go to measurement, shows me the samples. If you don't want to use, let's say you only want to use Osmond for a few of these, maybe you only want to use one just sample per channel, that's okay. Maybe that's all you have to work with. You can go to the test and just say 0. Putting 0 will take that one out because it's no longer going to be measured with 0 seconds there. What you're going to want to do for each sample is you're going to want to run each sample to get the count rate so we know what counts we're using, and to also calculate what measurement time is necessary for the drift monitor. Right now we don't know what the counting statistical error is running at 2 seconds. So what we always do is we'll go here, we'll save, and then we'll go back to the measure window. And if you go to the measure tab that's next to measure batch, you can go ahead and just do a manual measurement. So if you take the Osmond sample and put it in a cup and put that cup right into the chamber, we can do a manual measurement. And if you go to that measure tab and you say the application, so test one, and you'll select instrument monitor or monitor as the sample type to be run, and you'll select you'll see Osmond and test one there. You'll select Osmond and then you'll say measure. Once you measure it, you'll get our initial count rates populated here. Okay, what you'll want to do is you'll want to take those count rates and you'll want to put them in an Excel spreadsheet like so. So the channel, and these are just made up count rates that I have. So our initial count rates here. So silicon is the example. I ran it for 2 seconds, and as you can see, this calculation here, 100 divided by the square root of B5 times C5 times 1,000 equals your counting statistical error in a percent. Okay, so your count rate times your time times 1,000 gives you weight percent counting statistical error. So we're always trying to reduce the counting statistical error, and generally I like to make it 0.03 or less. So what I like to do is I like to see how much time do I need to make it that. Pretty close, 26 seconds, not bad. So then in there I would go ahead and I would do that for all of these. Okay, just play with these here, and this is a total sum. Again, just keep in mind how long these have to run for. And so when I go in here and I see, okay, 26 seconds isn't enough for that guy, let's bump it up a little bit more, maybe 40 seconds. Okay, still not enough. Let's say 120. Getting closer, not bad. You might want to cap it out at 100. Maybe that's too long to wait 2 minutes sitting there for one element. That's okay. So just keep going there and work through these, and you'll have your total times. And you come back in here and you'll populate the measurement times necessary for each channel. Okay, and we'll go back to parameters because we don't want our initial count rates for the 2 seconds. So we'll go back to parameters and we'll just say reset the monitor, and it's going to give you this warning. It'll erase all intensities. You don't have to calibrate again. Don't worry about it. You don't have to recalibrate it again. You say yes, and you come back to measurements, and now you have zeros. Okay, 0 for our initial, and you have all your times that you put in, that you adjusted, and now you're going to run the monitor. Okay, now you run the Osmond, and you get real R initial counts for the time that you told it to sit on each channel. So you would do it for both these samples here, or if you have more samples, for all of the samples that you have there. Okay, that's how we're going to do the instrument monitor program. One question that is asked a lot is, how often do I need to run the instrument monitor? And if anybody tells you a specific time, well, that doesn't make any sense because that's just arbitrary. So if somebody says you need to run it once a day, 2 times a week, once a month, once every 3 months, it's not based on data. So have a QC sample and have a plus minus for that sample that you identify as being acceptable. If it falls outside of that range, go ahead and run your drift monitor. Drift monitor programs are used to change the slope or the the y-intercept there of the calibration line. Again, you do not have to rely on a drift monitor program if you do not want to. You could go ahead and just remeasure the standards again and get new count rates for the calibration and go ahead and calibrate that line again, just like we talked about prior in the calibration here. So if you remeasure the measurements, you'll have new measurement status screen here with the dates of when you measured the last measurements for those standards, and then you can go there and you can go ahead and calibrate them over again. So various ways there to work with the instrument monitor if you so choose to use it. Generally, people like to put a threshold on how much they want the drift monitor to correct. So if your slope difference is going far away from 1, then it might be time to go ahead and run the standards again and then get a new calibration line there. Okay. Just something here before we wrap it up. The wax additive there that we used, you can change that setting if you go to additives, and if you, let's say you have a wax or some other binder that you're using that's not included on this list, you can go ahead and add it and it will be included for you to use. You can also do the same thing for films if you're using a liquid cup for powders or liquids, and if the film is not here, you can go ahead and add it and it will be used accordingly for each of the standards. So that is how you create standards, applications, calibration, and instrument monitor. I hope this video helps you. If you have any questions, please call the 1-800 number and you will get in touch with an XRF application specialist or scientist, and we will help you with any of your questions. Alright, thanks. You have a nice day. Bye.